Hello everyone, and welcome back to another Geostats lecture video. And in this lecture video, I want to talk about the two possible significance tests for Morans eye. Right. The two possible significance tests for Morans eye. So just to sort of recap from our previous video, we went through the equation for Morans eye and sort of what it meant. And in this video, I want to talk about how we can determine if it's statistically significant. And it's important to note here that there are two different approaches that we can take in terms of what the p-value means in terms of the null hypothesis, right? There's two different null hypotheses that we can test. So the first possible test is what's called randomization. Right, so randomization, right, this is going to assume, right, the null hypothesis here is going to assume that the data, actually I suppose I should be very technical about this, right, is that every possible permutation of data values is equally likely. Right, every possible permutation of data values is equally likely. Well, what does this mean? This basically means that you could take your data set, right? Again, speaking about the R example that we've gone through so far, right? We could take the percent rural of any county and we could shift them around. We could shake up the data set and we could move the percent rural value from one county and give it to another and vice versa. We could move all the values around, and that any one of those combinations would be just as likely to happen as the one that we actually see. Hopefully that makes sense. Basically, what we're saying is that the value in a particular county doesn't matter relative to any other value from any other county that we could have, right? Put another way, right? Any county could have any value in the data set and it wouldn't affect our Morans eye. That's what we're saying here for randomization, right? Is that it doesn't matter which value goes with which observation. That's what randomization is saying. So that's the first null hypothesis. And this is the one that sort of by default is used in most testings, is that, hey, it doesn't matter which data value I have from the data set, right? Me as an observation, I don't care which data value I get. It doesn't matter to me. You can give me that counties, you can give me that counties, you can give me that counties, and my Morans eye will not significantly change. That's the first null hypothesis. So ideally here, right, if we reject this null hypothesis, right, if our p-value is less than 0.05, right, we reject the null hypothesis, right? So the alternative hypothesis would be that, right, possible permutations are not equally likely. Is not equally likely, which is basically saying, hey, I'm a county and my data value matters to me, right? I am not able to just take some other county's data value and be the same, right? It matters. So what this means, right, if every possible permutation is not equally likely, right, that's an indication that there is structure that matters, right? It matters to me what my data value is. So that's an indication, right, that our Morans eye statistic is actually telling us that we have a meaningful structure. And that meaningful structure is, at least in part, because of spatial autocorrelation. So hopefully that makes sense, right? Randomization, again, this is the default in most hypothesis testing for Morans eye. And again, we're just saying that the data value associated with a particular observation cannot be switched out, right? It is going to impact our results if we change out the values for observations. Hopefully that makes sense. Let's talk about the other test, right? Because there's a second test we can do, right? And this is normality. Right? We've already kind of seen normality before when we talked about normally distributed data. And essentially we're testing the same thing here. Right? We're saying in the null hypothesis, right, that all observations come from a single normally distributed population. Right, and the alternative hypothesis here is that they don't. Right, and again, right, p-value of less than 0.05 rejects the null hypothesis. But let's talk about what normality means in this case, right? If the data was normally distributed, we would expect that the majority of the values would have sort of an average, and that the extreme values would be less or more likely. Or I'm sorry, the extreme low and the extreme high values would be less likely overall. Let's talk about spatial autocorrelation for a second. Right? If spatial autocorrelation is a thing, right, we would expect to see pockets of values. Right? They wouldn't be normally distributed. We would have clusters of values. And so if we reject the null hypothesis, if we reject the idea that these observations are from a single normally distributed population, right, that's indicative that we actually don't have a normal distribution. Right? And that's indicative that, again, we have a structure to our data set, and our structure is not normal. And with Morans I, right, we're specifically saying that we're assuming that that structure comes from spatial autocorrelation. So hopefully this makes sense, and hopefully you can see why, by and large, randomization is the default, because this one sort of makes a little more sense in terms of testing for spatial autocorrelation, because we're saying that the data value is specifically tied to its observation, that we can't swap them around, which would be a strong indication that the observation needs its data value, which means that we have a structure, and that structure is likely, again, coming from spatial autocorrelation. So hopefully this makes sense. And as always, please reach out. Thank you.